Right now, you are plummeting through an infinite ocean of darkness at speeds that would tear apart anything in its path. Since you began reading these words, you have already crossed thousands upon thousands of miles through the void. But here is what keeps scientists awake at night. We have absolutely no idea why. Something out there, something invisible and impossibly massive, is dragging our entire galaxy toward it, like a leaf caught in an invisible current. And it is not just our galaxy. Hundreds of thousands of other galaxies are being pulled toward the exact same point in space. You have never experienced true stillness. Not for a single moment in your entire existence. This is not poetry or metaphor. This is documented, measurable, scientific reality. At this very instant, you are rocketing through the cosmos at a velocity so extreme it defies human comprehension, nearly 900,000 miles per hour. That is how fast our galaxy is traveling through the universe, carrying you along with it whether you realize it or not. Let me give you a sense of scale that might actually register in your mind. A high-powered rifle bullet screams through the air at roughly half a mile every second. That seems fast. That seems like the upper limit of speed you could ever hope to experience. But you are currently moving approximately 800 times faster than that bullet, every single second of every single day. In the brief moment it takes you to complete a single blink of your eyes, you have traversed roughly 150 miles through space. By the time you finish reading just this opening section, you will have crossed a distance greater than twice the circumference of Earth, and your body registers none of it. No sensation of movement, no cosmic wind pressing against your face, no feeling of acceleration or velocity or motion of any kind. You sit in perfect stillness while the universe streams past you at incomprehensible speeds. This discovery emerged in the 1,970 seconds when astronomers turned their instruments towards something that has been traveling through space since the birth of existence itself. They call it the cosmic microwave background radiation. Imagine it as the fossilized echo of creation. Nearly 14 billion years ago, when the universe exploded into being, it released a pulse of light so intense it illuminated all of existence. That light has been racing through space ever since, stretched thin and cooled by the relentless expansion of reality itself. Today, it permeates every cubic inch of the cosmos as a faint whisper of microwave energy. Scientists expected this ancient glow to appear identical in every direction. After all, the universe should be fundamentally uniform on the largest scales. No preferred direction, no cosmic up or down, just endless sameness extending in all directions forever. But when they measured this primordial radiation with sufficient precision, they discovered something that should not have been there. The light was subtly different depending on which direction they looked. In one particular region of the sky, the radiation appeared slightly bluer than average. In the opposite direction, it appeared slightly redder. You experience this same phenomenon every time an emergency vehicle rushes past you on the street. As the ambulance approaches, the sound waves compress, making the siren pitch higher. As it speeds away, the waves stretch, making the pitch drop lower. This is the Doppler effect, and it applies to all waves, including light itself. When you move toward a source of light, the waves compress and shift toward the blue end of the spectrum. When you move away, they stretch and shift toward red. The pattern encoded in the cosmic microwave background told astronomers something extraordinary and deeply unsettling. Our entire galaxy was moving, not just drifting randomly through space, but traveling in a very specific direction at tremendous velocity. This initial finding did not immediately alarm anyone. After all, the universe is expanding. Everything is moving away from everything else in a grand cosmic tide first documented by Edwin Hubble in the 1,920 seconds. Scientists naturally assumed our motion was simply part of this universal expansion, just the normal flow of space carrying our galaxy along like flotsam on an infinite ocean. But when they performed the calculations, the numbers refused to cooperate. Yes, the expansion of the universe accounted for some of our velocity. And yes, the gravitational influence of nearby galaxies like Andromeda explained a bit more. But even after accounting for every known force and influence, there remained a massive component of our speed that made absolutely no sense. We were moving too fast. And we were moving in a direction that had no obvious explanation. Something else had to be out there, something hidden from view, something with enough gravitational power to yank an entire galaxy off its expected course. The scientists checked their instruments, They verified their calculations. They looked for errors in their methodology, but the result remained consistent no matter how many times they ran the numbers. An invisible force was pulling us through space, and they had no idea what it could possibly be. The answer would require decades of research, new technologies, and observations of unprecedented precision. And when scientists finally pieced together what was actually happening, it opened questions far more disturbing than the original mystery. To understand what researchers ultimately discovered, you first need to grasp exactly how they made these measurements. The cosmic microwave background is not just ancient light. It represents the oldest photons in existence. The very first light particles that were ever able to travel freely through space without immediately colliding with matter. Here is what happened in those first chaotic moments after the universe burst into existence. For several 100,000 years, reality was so unimaginably hot and dense that light could not propagate anywhere. Photons would flash into existence and instantly slam into particles of matter, getting absorbed or scattered before they could travel even the smallest distance. The entire universe was effectively opaque, like trying to see through an infinite fog so thick that no light could penetrate more than a fraction of an inch. Then something fundamental changed. As the universe continued expanding, it also cooled. Eventually, approximately 380,000 years after the moment of creation, temperatures dropped enough for atoms to form. Electrons that had been flying around as free particles suddenly became bound to atomic nuclei. This created gaps in space. This allowed light to travel. In that pivotal instant, the universe transformed from opaque to transparent, and the light that was released in that moment has been traveling ever since. For nearly 14 billion years, those ancient photons have been crossing the void, stretching as space itself expanded, cooling from a blazing white brilliance to an invisible microwave hum. When scientists first detected this radiation in 1965, it represented one of the most profound discoveries in the history of human knowledge. It confirmed that the universe had a definite beginning. It validated the Big Bang theory, and it provided humanity with an actual snapshot of what the cosmos looked like when it was barely more than an infant. But the cosmic microwave background held additional secrets. Secrets that would not reveal themselves for years. When astronomers created detailed maps of this ancient light across the entire sky, they anticipated finding perfect uniformity. The early universe should have been smooth and featureless, with identical temperatures everywhere. Instead, they found subtle variations. Some patches of sky registered as slightly warmer. Other patches appeared slightly cooler. The differences were incredibly tiny, just a few millionths of a degree. But they were real, and they were measurable. These minute fluctuations would later prove to be the seeds of everything we observe in the modern universe. The slightly denser regions eventually collapsed under their own gravity, forming galaxies and stars and planets. The slightly less dense regions expanded into the vast empty voids that separate cosmic structures. But there was another pattern hidden within this data, a much larger pattern that would change our understanding of our place in existence. When scientists analyzed the overall temperature distribution of the cosmic microwave background, they noticed that one entire hemisphere of the sky was consistently warmer than the opposite hemisphere. This was not a random fluctuation. This was not an artifact of measurement error. This was direct evidence of motion. Our galaxy was plowing through this sea of ancient light at phenomenal speed, and the direction of that motion pointed toward one specific region of the sky, a particular patch in the constellation Centaurus. Something in that direction was exerting enough gravitational influence to affect the movement of our entire galaxy across distances spanning hundreds of millions of light years. Scientists had detected something monstrous. Now they needed to determine what it actually was. Let us pause and consider what this velocity means for you on a personal level. 900,000 miles per hour sounds abstract. It registers in your mind as just another large number among countless large numbers. Your brain files it away without really processing the staggering enormity of what it represents. So allow me to make it concrete and immediate. If you have been reading this for approximately 1 minute, you have already traveled roughly 15,000 miles through space. That represents more than half the distance around the entire planet Earth. By the time you finish reading this section, you will have crossed approximately 250,000 miles. That is roughly the distance from Earth to the Moon. And you did not feel a single thing, not the slightest hint of motion or acceleration or movement through space. Consider the last time you traveled in a vehicle on a highway. At 70 miles per hour, you could sense the vibration of the engine, watch the scenery blur past your window, feel the occasional bump or swerve in the road. Now imagine traveling more than 10,000 times faster than that. You should be experiencing forces so extreme they would instantly destroy your physical body. Your skin should be peeling back from the sheer resistance of space. Your bones should be shattering under acceleration. Every molecule in your body should be experiencing catastrophic stress. Instead, you feel absolutely nothing. You could be floating in perfectly calm water for all the sensation your nervous system reports. This occurs because motion is fundamentally relative. When everything around you moves at the same speed in the same direction, there exists no way to perceive that movement. The air molecules in your room are traveling with you. The ground beneath your feet is traveling with you. The entire planet, the complete solar system, the whole galaxy is traveling with you. From your personal frame of reference, you remain perfectly motionless. It is the rest of the universe that appears to be rushing past. But here is where the situation becomes genuinely unsettling. This is not random drift through empty space. We are being pulled in one specific direction. Something out there has metaphorically sunk its gravitational hooks into our galaxy and is reeling us in like a fish caught on an invisible line. Every single second that passes, we get 250 miles closer to whatever that something might be. Every minute brings us nearly 15,000 miles closer. Every hour, more than 800,000 miles closer. By the end of this day, you will be more than 20 million miles closer to the mysterious force that is dragging our galaxy through the void, and your sensory systems will register none of it. Scientists confirm this movement is absolutely real. They confirmed the direction remains consistent across all measurements. They confirmed we are accelerating toward a specific point in space. What they initially could not confirm was what exactly existed at that point. The numbers suggested something impossibly massive. Something with more gravitational pull than anything previously observed. Something that seemed to violate the rules governing what should be possible in our universe. They gave it a name that sounds almost whimsical, almost playful in its simplicity. They called it the Great Attractor, but there was nothing whimsical about what came next. Scientists are fundamentally comfortable with uncertainty. They expect it as part of the process. The universe is vast beyond measure and impossibly complex, and there will always exist phenomena we do not yet understand. This represents the normal state of scientific inquiry. But there exists a profound difference between not understanding something and having your understanding actively contradicted by every piece of evidence you gather. That is precisely what happened with the Great Attractor. When astronomers first calculated the velocity of our galaxy through space, they assumed the explanation would be relatively straightforward. The universe contains countless gravitational influences, after all. Nearby galaxies exert their pull on us. Distant galaxy clusters contribute their own forces. The overall expansion of space affects every object's motion through the cosmos. Simple physics suggested that adding up all these known influences should produce a number matching what we actually observe. Except the numbers refuse to match, not even remotely close. The Milky Way belongs to what astronomers designate as the local group. This represents a collection of approximately 40 galaxies bound together through mutual gravitational attraction. Our galaxy and Andromeda serve as the two dominant members, with dozens of smaller dwarf galaxies orbiting around them, like moons around planets. The local group, in turn, comprises part of a significantly larger structure called the Virgo cluster, which contains more than 1,000 galaxies spread across millions of light-years of space. Scientists could measure the gravitational pull emanating from all these objects with considerable precision. They knew the mass of each major galaxy. They knew the distances separating them. They knew exactly how much gravitational force each one should exert on our motion through space. When they performed the calculations, they discovered that these known influences could account for perhaps half our observed velocity, but not all of it. Not even close to all of it. We were moving hundreds of miles per second faster than the known gravitational sources could possibly explain. This left only two plausible interpretations. Either our fundamental understanding of gravity was completely wrong, or there existed something massive out there that we had not yet detected. Something hidden, something enormous beyond comprehension. Most scientists proved reluctant to abandon gravity as a theory. Einstein's general relativity had been tested countless times across nearly a century of observations, and it had passed every single test with remarkable precision. It predicted the motion of planets with extraordinary accuracy. It explained how light bends around massive objects. It even predicted the existence of black holes decades before technology advanced enough to observe them directly. Gravity worked. The mathematics worked. The predictions worked. So if gravity itself was not the problem, then the mass had to be real. There had to be something out there in the direction of the constellation Centaurus, something containing enough matter to yank our entire galaxy off its expected trajectory. The estimated mass required to produce the observed gravitational effect was staggering beyond belief. This mysterious object would need to contain the equivalent of 10 quadrillion stellar masses. That represents a 10 followed by 15 zeros. More mass than thousands of entire galaxies combined into a single region of space. At the time of this discovery, nothing in the known universe approached that scale. The largest black holes contained billions of stellar masses, not quadrillions. The most massive galaxy clusters might approach a few trillion stellar masses, but even those fell dramatically short of what would be required. Whatever the Great Attractor was, it represented something bigger than anything humanity had ever imagined. And we had absolutely no idea what it could be. Here's where the story takes a genuinely disturbing turn. Initially, scientists hoped the Great Attractor might represent a local phenomenon. Perhaps something in our immediate cosmic neighborhood was affecting only the Milky Way and a handful of our closest neighbors. That would still qualify as strange, certainly, but it would be manageable. A localized mystery proves easier to solve than a universal one. You can isolate variables, you can test specific theories. You can eventually narrow down the possibilities. But when astronomers began measuring the velocities of other galaxies throughout our region of space, they discovered something far more alarming. It was not just us. It was not just our immediate neighbors. Every single galaxy they measured in every direction surrounding the Great Attractor was moving toward the exact same point. Not dozens of galaxies, not hundreds. Thousands upon thousands of them stretching across unimaginable distances. Current estimates suggest that approximately 100,000 galaxies are being pulled toward the Great Attractor. These galaxies span a region of space more than 500 million light-years across. They include spiral galaxies, like the Milky Way. They include giant elliptical galaxies. They include dwarf galaxies barely visible from our position. They include irregular galaxies that defy classification, different ages, different compositions, different evolutionary histories. And yet every single one of them is moving in the same direction, all being dragged toward the same invisible point in space. Try to genuinely picture the scale of what this represents. A single galaxy contains hundreds of billions of stars. Each of those stars potentially hosts planets, moons, asteroids, comets, and countless other objects. The total amount of matter contained within a single galaxy exceeds human comprehension by factors so large they become meaningless. Now multiply that incomprehensible amount by 100,000. All of that matter. All of those stars. All of those worlds being pulled through the void by a single gravitational source. Whatever the Great Attractor is, it possesses enough power to influence a significant fraction of the entire observable universe. This realization eliminated most of the obvious explanations that scientists had been considering. A single massive black hole, even the largest one imaginable, could not produce this effect. The numbers simply did not work. A rogue halo of dark matter would not contain enough concentrated mass in one location. A hidden galaxy cluster might come closer to explaining the observations, but the mathematics still refused to fully cooperate. Scientists found themselves forced to consider increasingly exotic possibilities. Perhaps the Great Attractor was not a single object at all. Perhaps it represented something more complex and distributed. Perhaps it was a structure of some kind spanning hundreds of millions of light-years, a concentration of mass unlike anything ever observed or theorized. But there existed a significant problem preventing further investigation, a problem that would frustrate astronomers for decades. Every time they attempted to point their telescopes at the region where the Great Attractor should be located, they encountered an impenetrable barrier. Something was blocking their view. Something was preventing them from seeing what lay in that crucial direction. The universe appeared to be hiding its greatest mystery behind a cosmic curtain, and for decades, scientists could not find any way to peek behind it. Before we proceed further, we need to discuss gravity in detail, because gravity represents the only force in the universe powerful enough to accomplish what the Great Attractor is doing. You probably believe you understand gravity fairly well. It keeps your feet planted on the ground. It makes dropped objects fall downward. It holds the moon in orbit around Earth. Simple and straightforward, correct? Not exactly. Gravity ranks among the most mysterious forces in nature. We can describe what it does with incredible mathematical precision. We can predict its effects across cosmic distances with remarkable accuracy. But we still do not fully understand what it actually is or how it fundamentally works at the deepest level of reality. Here is what we know with absolute certainty. Every object possessing mass creates gravity. The more mass an object contains, the stronger its gravitational pull becomes. And crucially, gravity has infinite range. Unlike other fundamental forces that fade to insignificance over short distances, gravity extends forever in all directions. It grows weaker with increasing distance, certainly, but it never completely disappears. It never reaches zero. This means that every single object in the universe is gravitationally connected to every other object, no matter how far apart they might be. Right now, at this very moment, you are being pulled ever so slightly by the gravity of distant stars scattered across the galaxy. You are being pulled by faraway galaxies billions of light years from Earth. You are being pulled by cosmic structures so remote that their light has not yet had time to reach us. The pull is unimaginably weak. Far too small to measure with any existing instrument. Far too small to produce any detectable effect on your body. But it exists nonetheless. It is real. It is happening right now. When we scale up from individual objects to entire galaxies, gravity becomes the dominant force shaping the cosmos. Galaxies do not drift through space randomly. They follow the gravitational contours of the universe itself, flowing like water down a hillside toward regions containing greater concentrations of mass. Think of space as a vast rubber sheet stretched tight in all directions. Every object possessing mass creates a dimple or depression in that sheet. Small objects make small dimples barely noticeable to anything nearby. Massive objects create deep craters that distort the sheet across significant distances. Everything on the sheet naturally rolls toward the deepest points, following the curved surface created by the presence of mass. The Great Attractor represents the deepest crater in our corner of the universe, a gravitational well so profound and so extensive that it pulls on everything within hundreds of millions of light years. But here is the genuinely terrifying part of this situation. Gravity does not just pull objects toward sources of mass. It also tells us something crucial about what is doing the pulling. The strength of any gravitational field is directly proportional to the amount of mass creating it. This relationship is precise and mathematical and unchanging. So when scientists measured how strongly the Great Attractor was pulling on surrounding galaxies, they could calculate how much mass it must contain. The answer that emerged from those calculations was 10 quadrillion stellar masses. That represents more mass than 50,000 Milky Way galaxies combined. More matter concentrated in one region than scientists thought could possibly exist based on everything they knew about cosmic structure formation. Something containing that much mass should be trivially easy to observe. It should be blazing with the light of trillions upon trillions of stars. It should dominate the night sky in its general direction. It should be one of the most obvious features visible to any telescope pointed anywhere near that region of space. And yet, when astronomers looked in that direction with their most powerful instruments, they saw essentially nothing. The Great Attractor was a gravitational giant somehow hiding in plain sight, and the reason for its invisibility was about to make the mystery exponentially stranger. Imagine attempting to study a distant mountain range while standing in the middle of dense fog so thick you can barely see your own hands. You know the mountains are there. You can feel the wind patterns coming off their slopes. You can detect their presence through indirect means. But no matter how hard you strain your eyes, you cannot actually see them through the obscuring haze. That represents exactly the problem astronomers faced when attempting to observe the Great Attractor directly. Our galaxy, the Milky Way, is a spiral structure roughly 100,000 light-years in diameter. Most of its 400 billion stars are concentrated along a relatively flat plane, forming the distinctive band of light we see stretching across the night sky when viewed from Earth's surface. This plane also contains vast clouds of interstellar dust and gas, the raw materials from which new stars are continuously being born. This dust creates a significant observational problem. When we attempt to look out into deep space through the plane of our own galaxy, all that dust and gas gets directly in the way. It absorbs visible light. It scatters photons in random directions. It makes seeing distant objects essentially impossible, like trying to look through a frosted window where the glass is present, but everything on the other side becomes just a blur of indistinct shapes and colors. Astronomers have given this obscured region a name that perfectly captures its effect on observations. They call it the zone of avoidance. It represents a band around the sky roughly 20 degrees wide where we essentially cannot see anything beyond our own galaxy using conventional telescopes operating in visible wavelengths. And it blocks our view of approximately 10% of the entire universe. Now, guess where the Great Attractor happens to be located? Right in the middle of the zone of avoidance. Almost exactly centered in the one part of the sky we cannot see clearly using normal observational methods. Initially, this seemed like catastrophically bad cosmic luck. Of all the possible locations in the sky where the Great Attractor could have been situated, it ended up in the one spot hidden from direct observation by our own galaxy's dust. Some scientists even wondered whether there might be a connection. Perhaps the same large-scale structures that created the dust concentrations in our galaxy were somehow related to whatever was causing the Great Attractor phenomenon. That speculation turned out to be incorrect. Our galaxy's orientation in space has nothing whatsoever to do with the large-scale structures existing far beyond it. We simply happen to end up in a position where the most massive gravitational influence in our cosmic neighborhood is blocked by our own galactic backyard. Pure coincidence. Terrible luck for astronomers trying to understand what was happening. For decades, this represented an seemingly insurmountable obstacle. Astronomers could measure the Great Attractor's gravitational effects with impressive precision. They could pinpoint its approximate direction in the sky. They could calculate its distance and mass within reasonable margins of error, but they could not actually see it directly. It was like knowing exactly where buried treasure is located, but being physically unable to dig it up. The Great Attractor remained a gravitational ghost. Felt through its effects but never directly observed. That situation persisted until scientists developed new methods to see through the cosmic fog. Let us discuss in more detail what actually blocks our view, because the specifics matter significantly. The interstellar medium is not empty vacuum. It contains incredibly thin gas and microscopic dust particles spread across the vast distances between stars. In most regions of space, this material is so sparse that it barely affects observations. A cubic inch of typical interstellar space might contain only a handful of atoms, essentially nothing. But when you are looking through hundreds or thousands of light years of this material, even tiny densities accumulate into significant obstacles. The dust particles create especially problematic interference. They typically measure smaller than a micron in diameter, about 100 times thinner than a human hair. Each individual particle represents almost nothing. But trillions upon trillions of them spread across thousands of light years create an effective barrier to visible light wavelengths. Think of it like looking through very light fog. Any single water droplet is essentially invisible to your eye, but enough droplets together and you cannot see more than a few feet in front of you. The individual obstacles are negligible. The cumulative effect is overwhelming. The gas in the interstellar medium causes different but equally frustrating problems. It absorbs light at specific wavelengths, creating dark lines in the spectra of distant objects that make analysis difficult. It also scatters blue light more efficiently than red light, causing distant objects to appear redder than they actually are. Astronomers call this phenomenon interstellar reddening, and it can make objects appear significantly fainter and more distant than their true properties. In the plane of the Milky Way, where most of this obscuring material is concentrated, both effects combine to create an almost impenetrable barrier to observation. Stars that should be easily visible become completely invisible. Galaxies that should appear as bright smudges disappear entirely from view. The universe beyond our galaxy simply fades to black in that direction. The zone of avoidance earned its name because early astronomers noticed that galaxies seemed to avoid this region of the sky. There were far fewer galaxies visible near the plane of the Milky Way compared to any other direction. Of course, the galaxies were not actually avoiding anything. They were simply hidden behind thousands of light-years of dust. They existed in the same densities as everywhere else. We just could not see them. For the Great Attractor, this created a profoundly frustrating paradox. Scientists knew something massive was there. They knew it was pulling on our galaxy and thousands of others. They could calculate its properties with reasonable precision using gravitational measurements, but they could not confirm its existence through direct visual observation. Some astronomers began to worry they might be completely wrong. Perhaps the Great Attractor was not a real physical object at all. Perhaps it represented an artifact of measurement errors or flawed theoretical assumptions. Without direct observation, there existed no way to be completely certain of anything. The mystery desperately needed new technology, new methods of observation, new ways of seeing what visible light could not reveal. And fortunately, the universe provides far more than one kind of electromagnetic radiation to work with. Visible light represents just a tiny slice of the complete electromagnetic spectrum. Our eyes evolved to detect this particular range of wavelengths because it happens to be the type of radiation that passes most easily through Earth's atmosphere and provides the most useful information for survival on our planet's surface. But the universe is absolutely filled with other kinds of electromagnetic radiation that remain completely invisible to human perception. Radio waves carrying information across vast distances. Infrared light radiating from warm objects. X-rays produced by extreme cosmic events. Gamma rays released by the most violent processes in nature. Each of these wavelengths can reveal information about the cosmos that visible light cannot possibly provide. And here is the crucial point that would eventually solve the Great Attractor mystery. Some of these wavelengths can pass through the dust and gas that blocks visible light in the zone of avoidance. They can penetrate the cosmic fog as if it barely existed. Radio waves prove especially effective at this. Their wavelengths are so much longer than the size of dust particles that they simply glide past these tiny obstacles without significant interference. A radio telescope can peer straight through the plane of the Milky Way, as if the obscuring dust were not even present. What appears as an impenetrable black barrier to optical telescopes becomes essentially transparent to radio observations. Infrared light also provides useful penetration, though not quite as complete as radio waves. Longer infrared wavelengths can pass through much of the dust that blocks visible light, revealing objects that are completely invisible in optical images. The shorter infrared wavelengths still experience some blocking, but even partial penetration represents a dramatic improvement over total opacity. Starting in the 1980 seconds, astronomers began conducting systematic surveys of the zone of avoidance using these new observational technologies. For the first time in human history, they could glimpse what lay beyond our galaxy's dusty veil in the direction of the Great Attractor. The results were absolutely extraordinary and completely unexpected. Radio surveys revealed thousands of previously unknown galaxies hiding behind the Milky Way, galaxies that had been completely invisible to every optical telescope ever pointed in that direction. Infrared observations uncovered massive galaxy clusters that had existed all along but remained hidden from human knowledge. The zone of avoidance turned out to be just as crowded with cosmic structures as any other region of the sky. We simply had not been able to see them before. And in the direction of the Great Attractor, astronomers discovered something genuinely remarkable. Not a single massive object, as some theories had suggested. Not a giant black hole lurking in the darkness. Not a rogue dwarf galaxy of unusual properties. Instead, they found an entire cosmic neighborhood hidden behind the curtain of dust. Thousands upon thousands of galaxies, all concentrated in a relatively compact region of space. All part of massive structures that humanity had never observed before this breakthrough. The Great Attractor was not hiding because it was small or dim or unusual. It was hiding because it was located behind us, obscured by our own galaxy's interstellar material. When the veil was finally lifted through radio and infrared observations, scientists realized they had been thinking about the Great Attractor incorrectly from the very beginning. It was not a thing. It was not a single object you could point to and say definitively, "There it is. That is what has been pulling us." The Great Attractor was something far bigger, far more complicated, and far more important to our understanding of the universe's large-scale structure than anyone had imagined. When astronomers finally pierced the zone of avoidance and observed what lay beyond, they expected clear answers to their questions. What they received instead was an entirely new set of mysteries that would take years to unravel. The region around the Great Attractor turned out to be absolutely crowded with galaxies, not just a handful of extra objects hidden by dust. Thousands of them packed together in dense concentrations that rivaled the most massive structures anywhere in the nearby universe. The first major discovery was something called the Norma Cluster. This represents a massive galaxy cluster located approximately 220 million light-years from Earth, almost exactly in the direction where calculations had placed the Great Attractor's center of mass. The Norma Cluster contains hundreds of individual galaxies, including several giant elliptical galaxies that dwarf the Milky Way in both size and total stellar population. For a brief moment, scientists thought they had finally found the answer. Perhaps the Norma Cluster was the Great Attractor. Perhaps all those galaxies combined contained enough mass to explain the mysterious gravitational pull affecting our motion through space. The numbers should work out. The location matched predictions. Everything seemed to fit together perfectly. But when they performed detailed calculations, the mathematics refused to cooperate. The Norma Cluster is undeniably massive. It contains trillions of stellar masses concentrated in a relatively small region of space. But that still falls far short of the 10 quadrillion stellar masses required to explain the Great Attractor's observed influence on surrounding galaxies. You would need dozens of Norma clusters all piled on top of each other to produce that kind of gravitational effect. One cluster, no matter how impressive, could not possibly account for what we were observing. Further surveys using radio and infrared wavelengths revealed even more structures in the region. The Norma cluster was not alone. It was surrounded by other clusters, other concentrations of galaxies, other massive structures, all packed into the same general region of space within the zone of avoidance. Scientists began to suspect that the Great Attractor was not a single object at all. It was not even a single cluster of galaxies. The Great Attractor represented an entire region of space where matter had been accumulating over billions of years, creating a gravitational basin so deep that everything else in the cosmic neighborhood was flowing toward it like water running downhill. This was a fundamentally different way of conceptualizing cosmic structures, not as isolated objects floating in empty space, but as parts of a vast interconnected web where gravity slowly pulls matter into ever larger concentrations over cosmic timescales. The Great Attractor was not a monster lurking in the darkness. It was a drain in the cosmic bathtub, a low point in the gravitational landscape where everything naturally flows over billions of years. But if that interpretation was correct, then the Great Attractor was merely one piece of an even larger puzzle, because drains do not exist in isolation. They are part of a system. They connect to other features in the landscape. What system was the Great Attractor part of? How deep did this gravitational rabbit hole actually go? And what did it reveal about the structure of the universe on the largest possible scales? To understand what the Great Attractor truly represents, we need to zoom out dramatically, way out, far enough to see the structure of the universe itself across distances that make galaxies look like individual grains of sand on an infinite beach. From Earth's surface, the night sky appears as a random scattering of stars with no apparent pattern or organization. But that represents an illusion created by our limited perspective and the relatively small region of space we can observe with unaided eyes. When astronomers map the positions of millions of galaxies across billions of light years, a pattern emerges that changes everything. The universe is not random at all. It possesses structure on scales so vast they challenge human comprehension. Scientists call this the cosmic web. It represents a vast network of filaments, walls, and nodes with galaxies clustered along the strands like dewdrops on a spider's web. Enormous empty voids exist in between these structures, containing almost no matter at all. If you could somehow see the entire observable universe at once from an impossible vantage point outside reality itself, it would look almost biological in nature, like neurons connected by axons forming a vast brain, like foam in a bubble bath where bubbles meet at edges and corners, like the structure of life itself but scaled up to cosmic proportions. This web did not form by accident or random chance. It represents a direct consequence of the physics that governed the early universe. When the cosmos was young, matter was distributed almost uniformly throughout space. Almost, But not quite. There were tiny fluctuations present from the very beginning. Regions where matter was slightly denser than average. Regions where it was slightly less dense than average. These fluctuations had quantum origins, random variations that got magnified to cosmic scales by the rapid expansion of space during the universe's first moments. As the universe aged over billions of years, gravity went to work on these initial fluctuations. The denser regions possessed slightly stronger gravitational pull, so they attracted more matter from their surroundings. The slightly emptier regions lost matter to their denser neighbors. Over billions of years, this process amplified the initial tiny variations into the dramatic structures we observe today throughout the cosmos. Dense regions became progressively denser. Empty regions became progressively emptier. Matter collected into filaments and walls while vast bubbles of nearly empty space opened up between them. The galaxies we see today did not appear randomly throughout space. They formed along the filaments of the cosmic web in the specific locations where matter was sufficiently concentrated. Galaxy clusters formed at the intersections of filaments where multiple streams of matter came together. Superclusters formed where multiple clusters gathered into even larger associations, spanning hundreds of millions of light years. The Great Attractor is not separate from this structure. It is fundamentally part of it, a particularly dense node in the cosmic web, where filaments converge and matter has accumulated over billions of years of gravitational evolution. Understanding this changes everything about how we conceptualize our place in the universe. We are not just in a galaxy floating randomly through empty space. We are on a strand of the cosmic web, being pulled toward a gravitational basin created by the structure of the universe itself. We are part of a flow that has been ongoing since shortly after the beginning of time. Let me walk you through the cosmic hierarchy step by step, because it helps explain what the Great Attractor actually represents in the grand scheme of existence. Start with a single star. Our nearest stellar neighbor, Proxima Centauri, lies approximately 4 light-years away. A single light-year represents roughly 6 trillion miles. So even the closest star exists at a distance that utterly defies human comprehension when measured in familiar units. Now zoom out significantly. Stars are not distributed evenly through space. They clump together into galaxies through mutual gravitational attraction. The Milky Way contains somewhere around 400 billion stars, all gravitationally bound together into a vast spinning disk structure, roughly 100,000 light-years in diameter. That number is so large, it becomes effectively meaningless to human cognition, but it represents our immediate cosmic home. Galaxies themselves are not distributed evenly either. They clump together into groups and clusters bound by gravity. The Milky Way belongs to a collection called the Local Group, which contains approximately 40 galaxies, including Andromeda, the Triangulum Galaxy, and dozens of smaller dwarf galaxies orbiting the larger ones. The Local Group spans roughly 10 million light-years from edge to edge. Zoom out further still. Galaxy groups and clusters themselves are not evenly distributed across space. They gather into superclusters, vast associations containing thousands of galaxies spread across hundreds of millions of light-years. For decades, astronomers believed the Milky Way belonged to something called the Virgo supercluster, a structure approximately 110 million light-years across, containing at least 100 galaxy groups and clusters all gravitationally associated with each other. But even superclusters are not the end of the hierarchy. In 2014, astronomers announced the discovery of an even larger structure that redefined our understanding of where we actually live in the cosmos. They gave it a name drawn from Hawaiian language, Laniakea, a word meaning immense heaven. And it fundamentally changed how we think about our cosmic address. Laniakea is not just a supercluster in the traditional sense. It represents a supercluster of superclusters, a vast basin of gravitational attraction containing over 100,000 galaxies spread across 520 million light-years of space. The Virgo supercluster, which astronomers once thought was our cosmic home, turned out to be merely one branch of this much larger structure, just one small part of a gravitational system so vast it defies comprehension. And here is the key point that ties everything together. The center of Laniakea, the gravitational focus point toward which all of its galaxies are flowing over cosmic time, is located in exactly the same place astronomers had identified as the Great Attractor decades earlier. The Great Attractor was never a mystery object waiting to be discovered. It was the heart of our cosmic home. The center of a structure so vast that we could not even perceive its full extent until we developed the technology to map the three-dimensional structure of the universe across hundreds of millions of light-years. The mystery was solved, but the implications of that solution were only beginning to emerge. Laniakea changed our understanding of where we exist in the universe at the most fundamental level. Before its discovery, astronomers thought of cosmic structures as fairly static and hierarchical. Galaxies belong to groups. Groups belong to clusters. Clusters belong to superclusters. Each level of the hierarchy was defined by gravitational binding, objects held together by their mutual attraction, orbiting common centers of mass. But Laniakea is different in a crucial way. It is not gravitationally bound together in the traditional sense. The galaxies within it are not orbiting a common center like planets around a star. They are flowing toward a common center. Think of it like a watershed on Earth's surface. When rain falls on a mountain range, the water does not stay where it lands. It flows downhill following the contours of the terrain, eventually collecting in rivers and lakes at the lowest points in the landscape. Different drops of rain might land miles apart on opposite sides of a valley, but if they are on the same side of the continental divide, they will eventually end up in the same river system. They flow together not because they are bound to each other, but because they are all following the same gravitational gradient downward. Laniakea is a cosmic watershed. The galaxies within it are like raindrops flowing along the gravitational contours of space toward the lowest point in the landscape. That lowest point, that gravitational drain, is what we call the Great Attractor. It is not pulling us through some mysterious force. It simply represents the bottom of the basin we happen to be sliding down. The boundaries of Laniakea are defined by this flow. Astronomers mapped the velocities of thousands of galaxies and identified where the flows diverge. Galaxies on one side of the boundary flow toward the Great Attractor, at the center of Laniakea. Galaxies on the other side flow toward different attractors, different gravitational basins with their own centers of mass. This represented a revolutionary way of thinking about cosmic structure. Instead of defining superclusters, by which galaxies are gravitationally bound together, scientists could define them by how galaxies are moving, by the direction of their flow through space. The cosmic web was not just a static structure frozen in time. It was a dynamic one, with rivers of galaxies flowing through it, like ocean currents circulating across Earth's surface. Our galaxy, the Milky Way, is part of this flow. We are one of approximately 100,000 galaxies sliding down the gravitational slope toward the center of Laniakea. We have been falling for billions of years since shortly after our galaxy first formed, and we will continue falling for billions more years into the distant future. But here is the strange and unsettling part of the story. Despite all that falling, despite billions of years of motion toward the center, we will never actually reach it. The universe has one more trick up its metaphorical sleeve, and it changes everything about our ultimate fate. Let me be absolutely clear about what scientists discovered, because it is remarkably easy to misunderstand the fundamental nature of what we are dealing with. The Great Attractor is not an object in any conventional sense. You cannot point a telescope at it and take a photograph of it as if it were a single thing. It does not possess a surface or a boundary or a specific location you could theoretically travel to and visit. The Great Attractor is a place, a region of space, a gravitational center of mass for an enormous cosmic structure spanning hundreds of millions of light years. Think about the center of mass of our solar system. It is not located at the visible surface of the sun at the center. It represents a mathematical point in space inside the sun, but not identical to any particular feature of the star itself. Everything in the solar system orbits around this point, pulled by the combined gravity of all the mass in the system. The sun itself wobbles slightly around this point as the massive planets exert their own gravitational influence. The Great Attractor works according to the same principle, just scaled up to incomprehensible proportions. It represents the center of mass of the Laniakea supercluster, the combined gravitational pull of 100,000 galaxies, all pointing toward a single region of space. There is no giant black hole there consuming everything that approaches. There is no alien megastructure warping spacetime. There is no mysterious dark energy source or exotic physics violation. There is simply a concentration of galaxies, clusters, and dark matter, all pulling on the surrounding universe with their combined gravity. The Norma cluster sits near this gravitational center, So do several other massive galaxy clusters that we have now mapped using radio and infrared observations. Together, they create the gravitational well that we have been calling the Great Attractor for decades. This might sound like an anticlimax after all the buildup. We spent decades searching for a mysterious cosmic monster, and it turned out to be just more galaxies, just ordinary matter concentrated in space. Nothing exotic or unprecedented or physics-defying. But that reaction misses the profound point of what was actually discovered. The real discovery was not what the Great Attractor is in terms of its physical composition. The real discovery was what the Great Attractor taught us about the universe, about how matter is distributed on the largest possible scales, about how gravity shapes the evolution of cosmic structures over billions of years, about our place in the vast hierarchy of existence. We are not floating randomly through empty space on an arbitrary trajectory. We are part of an enormous system, a vast supercluster with a defined center and defined boundaries. We are flowing toward that center, along with 100,000 other galaxies, following gravitational currents that have been flowing since the universe was young. The Great Attractor was never a monster waiting to devour us. It was a signpost pointing toward our cosmic home, a marker showing us where we fit in the grand structure of existence. And yet there is one final twist to this story, one last mystery that makes everything more complicated and more fascinating than the simple resolution might suggest. 10 quadrillion stellar masses. That represents the estimated mass of the Great Attractor. The combined gravitational influence pulling 100,000 galaxies toward the center of Laniakea. Let me put that number in perspective using comparisons that might actually register in human cognition. The Milky Way contains roughly 400 billion stars. Many of those stars are smaller than our Sunday. Some are significantly larger. But, averaged across the entire galaxy, the total mass works out to approximately 1 to 2 trillion stellar masses when you include all the stars, gas, dust, planets, and everything else made of normal matter. 10 quadrillion equals 10,000 trillion. That means the Great Attractor contains the equivalent of 5,000 to 10,000 Milky Way galaxies worth of mass. Now here is where the numbers become genuinely puzzling. There are about 100,000 galaxies in the Laniakea supercluster. If you add up all their visible mass, all the stars and gas and dust we can actually observe, you get perhaps 500 trillion stellar masses. Impressive, certainly, a number so large it defies human comprehension. But still far short of 10 quadrillion, still missing roughly 95% of the mass that must be present to explain the gravitational effects we observe. Where does the extra mass come from? The answer is dark matter, that mysterious substance that does not emit, absorb, or reflect any form of electromagnetic radiation, but still exerts gravitational influence on everything around it. Scientists estimate that dark matter makes up approximately 85% of all mass in the universe. For every pound of normal matter, atoms and molecules and everything we can see and touch and measure directly, there exist roughly 5 pounds of dark matter that remain invisible to all our instruments except through gravitational effects. The Laniakea supercluster is swimming in dark matter. It fills the spaces between galaxies like an invisible ocean. It surrounds galaxy clusters in enormous diffuse halos extending far beyond the visible boundaries. And it contributes the vast majority of the gravitational pull that defines the Great Attractor. This is confirmed science, not speculation or theoretical guesswork. We can observe the effects of dark matter in the rotation curves of galaxies, where stars orbit faster than visible matter alone could explain. We can see it in the way light bends around massive galaxy clusters, distorted by gravitational lensing from invisible mass. We can detect it in the structure of the cosmic microwave background itself, where dark matter's gravitational influence shaped the formation of the first structures in the early universe. Dark matter is real, even though we do not yet know what particles it consists of. Even though every experiment designed to detect dark matter directly has come up empty so far, even though it remains one of the greatest unsolved mysteries in modern physics. So, the Great Attractor's enormous mass is not unexplained. It comes from the combination of visible galaxies and the dark matter that pervades the supercluster, like an invisible scaffolding. But understanding where the mass comes from does not make the Great Attractor any less impressive or significant. A gravitational well containing 10 quadrillion stellar masses pulling on everything within 500 million light-years remains staggering beyond belief. Even with all our explanations and measurements and theoretical understanding, the scale remains almost impossible to truly comprehend, and we are falling into it at 900,000 miles per hour. Let us discuss distance because it matters critically for what comes next. The center of the Great Attractor is located approximately 200 million light-years from Earth. That sounds like an unimaginably enormous number. And in human terms, it absolutely is. Light traveling at 186,000 miles per second would need 200 million years to make the journey. But in cosmic terms, 200 million light-years qualifies as fairly close, practically neighboring by the standards of the universe. The observable universe extends approximately 46 billion light-years in every direction from our position. The Great Attractor sits roughly in our cosmic backyard, a nearby structure in the grand scheme of cosmic distances. This relative closeness actually matters significantly. If the Great Attractor were billions of light-years away, its gravitational influence on our motion would be negligible. Gravity weakens with distance following an inverse square law. Double the distance, and the gravitational pull drops to 1/4. Triple the distance, and it drops to 1/9. At 200 million light-years, the Great Attractor is close enough to exert a significant gravitational effect on our galaxy's motion. Not an overwhelming effect that dominates everything else, but a measurable one that we can detect through careful observations. That is why we are moving toward it at 900,000 miles per hour instead of some much smaller velocity. The travel time at our current speed would be approximately 150 billion years if nothing changed. If we just kept falling toward the Great Attractor at our current velocity without any other forces interfering, our distant descendants might eventually reach the center of Laniakea billions of generations from now. But something will change. Something is already changing even as we speak. The universe is not static. It is expanding. And the rate of that expansion is accelerating in ways that will fundamentally alter our trajectory. Every year, the space between distant objects grows larger. Objects that are far apart today will be farther apart tomorrow. For nearby objects like our galaxy and Andromeda, this expansion is negligible. Gravity overwhelms the expansion of space, and we are actually moving toward each other on a collision course. But for objects hundreds of millions of light-years away, the expansion starts to matter significantly. The Great Attractor is pulling us toward it with tremendous gravitational force. But the expansion of the universe is pushing us away by stretching the space between us. Right now, at this moment in cosmic history, the gravitational pull is stronger than the expansion push. We are gaining ground. Every year brings us closer to the center of Laniakea. But that will not always remain true. The balance is shifting. And when it finally tips, everything changes for our cosmic future. Here is something that would have seemed utterly impossible just 1 century ago. The universe is expanding, not into something else, not spreading out through some pre-existing space, everywhere at once. Space itself is stretching, carrying galaxies along with it, like raisins in rising bread dough that expands in all directions simultaneously. Edwin Hubble discovered this in 1929 when he observed that distant galaxies were all moving away from us. The farther away a galaxy was located, the faster it appeared to be receding. This was not because we occupy some special central position in the universe. It was because space itself was growing. Every point in space is moving away from every other point as the fabric of reality stretches. Imagine drawing dots on a balloon and then inflating it. Every dot moves away from every other dot, not because the dots are traveling across the balloon's surface, but because the surface itself is expanding underneath them. That describes what is happening to our universe on the grandest scales imaginable. For most of the 20th century, scientists assumed this expansion was slowing down. After all, gravity pulls everything together. The mutual attraction of all the matter in the universe should be acting like a brake, gradually reducing the expansion rate over billions of years. Eventually, many physicists thought the expansion might even stop completely or reverse, causing the universe to collapse back on itself in a big crunch. In 1998, 2 independent teams of astronomers set out to measure exactly how much the expansion was slowing down. They studied a particular type of exploding star called a Type Ia supernova, which always produces roughly the same amount of light. By measuring how bright these explosions appeared from Earth, they could calculate precise distances, and by measuring how much their light was redshifted, They could determine how fast they were receding. What they discovered shocked the entire scientific community and changed our understanding of the universe's fate forever. The expansion was not slowing down at all. It was speeding up, accelerating. The universe was expanding faster and faster over time, as if something was pushing it apart and overcoming the attractive force of gravity. Scientists name this mysterious force dark energy. They have no idea what it actually is. It does not fit into any existing theory of physics. It makes up roughly 68% of the total energy content of the universe. And yet we cannot detect it directly, cannot explain where it comes from, and cannot predict with certainty what it will do in the future. All we know is that it exists and that it is winning the battle against gravity. This discovery earned the leaders of those two research teams the Nobel Prize in Physics. It also fundamentally changed our understanding of the universe's ultimate fate. And it has direct implications for our journey toward the Great Attractor, because if the expansion of space is accelerating, then eventually that expansion will overpower the gravitational pull currently dragging us toward the center of Laniakea. The race between gravity and dark energy is on, and dark energy is going to win. Let me explain exactly what is happening, because the physics here is genuinely strange and counterintuitive. Right now, at this moment, we are moving toward the Great Attractor at 900,000 miles per hour. That velocity is real. It is caused by the gravitational attraction of the mass concentrated at the center of the Laniakea supercluster. If nothing else were happening, we would continue falling toward that center forever, eventually reaching it in approximately 150 billion years. But something else is happening. The space between us and the Great Attractor is expanding. This expansion is subtle at short distances. Between Earth and the nearest stars, space expands by only a few inches per year, far too small to notice or measure with any existing technology. But over larger distances, the effect accumulates dramatically. Between us and the Great Attractor, space is expanding by millions of miles every year. Currently, our velocity toward the Great Attractor exceeds the expansion rate of the space between us. We are winning the race. We are gaining ground. Every year brings us slightly closer to the center of Laniakea than we were the year before. But the expansion is accelerating. Every year, space grows a little bit faster than it did the previous year. The gap is closing, and at some point in the distant future, the expansion rate will exceed our velocity. The space between us and the Great Attractor will start growing faster than we can cross it. When that happens, we will start moving backward in a sense. Not in any physical sense. We will still be traveling toward the Great Attractor at tremendous speed, but the space we are traveling through will be stretching faster than we can traverse it. It will be like running on a treadmill that keeps accelerating. No matter how fast you run, if the treadmill speeds up faster, you fall further and further behind. You are still running forward at maximum effort, but you are moving backward relative to the goal. This is not science fiction or speculation. This is confirmed cosmology supported by decades of observations and theoretical work. The accelerating expansion of the universe will eventually overcome the gravitational pull of even the largest structures. The Great Attractor will slip away from us. The center of our supercluster, the place we have been falling toward for billions of years, will recede into the distance beyond our reach. And there is nothing we can do about it. Nothing any civilization anywhere could do about it. Gravity gave us a destination. Dark energy is taking it away forever, but the consequences go far beyond missing our appointment with the Great Attractor. Because the accelerating expansion will not just affect our journey to Laniakea, it will affect everything everywhere across the entire observable universe. There exists a boundary in the universe that most people have never heard of. Scientists call it the cosmic event horizon, and it represents the ultimate limit of what we can ever observe or reach, regardless of how long we wait or how advanced our technology becomes. The concept is similar to the event horizon of a black hole. Once something crosses a black hole's event horizon, it can never escape. The gravity is too strong. The escape velocity exceeds the speed of light. Even light traveling at the fastest possible speed cannot outrun the pull. The cosmic event horizon works differently, but produces the same result. It represents the distance at which the expansion of space equals the speed of light. Beyond this boundary, objects are receding from us so fast that their light will never reach us no matter how long we wait. They are not traveling faster than light through space, which physics forbids. Space itself is carrying them away at an effective speed greater than light can overcome. Today, the cosmic event horizon lies roughly 16 billion light-years away. Objects beyond that distance are effectively cut off from us forever. We will never see them, never visit them, never receive any signal from them. They exist, certainly, but they are permanently beyond our reach, permanently outside our observable universe. And here is the genuinely terrifying part. The cosmic event horizon is shrinking. As the expansion of the universe accelerates, more and more objects are crossing beyond the horizon into permanent invisibility. Galaxies that were once within our observable universe are being swept away, their light stretched to infinite wavelengths, their existence erased from our sky. This process unfolds slowly on human timescales. It is imperceptible across generations or even across millennia, but over billions of years, it will transform the observable universe. The Virgo cluster, a nearby concentration of galaxies just 50 million light-years away, will eventually cross the horizon and disappear from view. So will the great galaxy clusters and superclusters that dot our cosmic neighborhood. One by one, they will slip beyond the boundary and vanish as if they never existed. Even the Great Attractor itself, the gravitational center we have spent this entire journey discussing, will eventually be lost. The expansion of space will carry it beyond our cosmic event horizon, and it will cease to exist as far as we are concerned. The universe will become smaller, not physically smaller, but observationally smaller. The bubble of reality we can access will shrink until only our immediate neighborhood remains visible, and eventually even that will not be enough to tell us the truth about where we came from. Thank you for taking this journey through the cosmos. We have traveled from the discovery of our motion through space, to the mysterious Great Attractor, to the vast structure of Laniakea, to the ultimate fate of the universe in an era of accelerating expansion. We have learned that we are not stationary observers, but participants in a cosmic flow billions of years in the making. We have discovered that we occupy a special moment in history, when the universe still reveals its secrets to those who look. You started this journey believing you were sitting still. Now you know you are hurtling through the cosmos at incredible speed, carried by forces set in motion at the beginning of time, falling toward a destination you will never reach. You are part of something vast, something ancient, something more beautiful and terrible than our ancestors could have imagined. And now you understand your place in it.